Dave, and thank you to the organizers of both this week and the program. Everything I'm going to talk about today is joint with Daryl Cooper and Leslie Mavrakis. Some of you saw me give a variation of this talk like a year ago, so you might be a little bored, but there's new stuff at the end. So, okay, so here is the overall idea. We're going to let T be a family of manifolds. Oh, also, I speak quickly, so if you need me to repeat something, just let me know. The goal, this is an idea that dates back to Thurston, is to find a finite construction kit with gluing rules, like a Lego set, so that the following is true. If we take the set of, let's say, sometimes I want to put closed or compact manifolds that can be built with the pieces of this Lego set, okay? That is exactly the family that you were looking for. Okay, so you start off with a family of manifolds, you find a construction kit, and not only can you make everything that you want in T from that construction kit, but you can't build anything else. Okay, so this is the term, the kind of like catchphrase to remember is build a family of manifolds with a Lego kit and don't build anything else. Okay, so I'm going to start with an example. Let's say I just use this cell structure on the circle where I'm just labeling 3 of the edges, R, B, and G, red, green, and blue. And let's say the family of manifolds that I'm looking for is all covers of this circle of degree bigger than or equal to 3. Okay, so here's my claim that this is my kit. Okay, this is the Lego kit. So first, it's not the full Lego kit because I need to give you the gluing rules, but these are the pieces in the kit. There's 5 pieces. And my claim is that with these 5 pieces and the following gluing rules, I can build exactly that family of manifolds. Okay, so what I'm going to give you the gluing rules now. What it means for I, when I put I glues to J, that means the end of the I piece and the start of the J piece are clicked together. They're identified. Okay, so I'm just going to give you a picture here of what that means. Oh, sorry. So first, I don't know why this is not working. Okay, there we go. What did that say? Okay, there we go. Okay, should be a 5. So let me just put that in. Okay, so these are the gluing rules. The piece 1 glues to piece 2, 2 glues to 3, 3 glues to 4, 3 glues to 5, 3 glues to 1, 4 glues to 1, and 5 glues to 1. There's actually something missing there. That's not every single possible gluing. So let me just show you an example of what I mean for 2 pieces to glue together. When I say that 1 glues to 2, I mean literally you take the blue piece and the green piece, line up the end of one and the beginning of the other, and click them together. Okay, and that's always going to be denoted by the dashed double colors. Okay, and here's another example. If you say, okay, I can glue the 3 piece to the 5 piece, similarly, you take the B edges at the end of one and the beginning of the other, and you click them together to create this big piece. It is S1, but like with more, so I took a triangulation of S1, right? I made it with the 3, like you can think of it as, yeah, all like simplicial covers or something, right? You want to actually construct a cover. I'll show you one in a second, but that really looks like RBG, 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 and closes up. This is also just the heuristic of like what the definitions are going to be later on. I'm just using this as a motivating example. So maybe just stick with me for another couple minutes and then you'll be a little happier. Yeah, exactly. Connected covers. Yeah. Yeah. Okay. So again, what's my claim? The set of closed manifolds that I can build with this kit. And let's put connected, right? So the set of connected closed manifolds that I can build with this kit is exactly the covers of this circle of degree bigger than or equal to 3. So the proof sketch, I'm not actually going to sketch the whole proof because it's just a motivational example, but you need to do 2 parts. First, you need to know that you can build all of the covers of degree bigger than or equal to 3. And then the second thing is to eliminate the other closed 1 manifold. So just eliminate the degree 1 and 2 cover, right? So here is an example that shows you how to build 2 covers, for instance. Okay, so on the, what is this? Your left-hand side, what I've done is I've glued piece 1 to piece 2 to piece 3 to piece 4 and then back to glue to piece 1. Okay, so you can see this here. This is the blue piece, the green piece, the pink piece, and the purple piece. When you glue them all up together in that order, and this is valid with the gluing rules, I get a cover of degree 4, which I can determine just by counting up the number of vertices. Okay. And similarly, if I want to make a degree 5 cover, I can glue piece 1 to 2 to 3 to 5, and then glue back to 1. And so here is a degree 5 cover. Blue, green, pink, and then instead of doing the purple at the end, they do the orange to get a degree 5 cover instead of degree 4 cover. Okay, this is just showing you two, but if you get bored, you can just play with this example and go construct, like, see how you construct all covers of degree 3K, 3K plus 1, 3K plus 2. It's going to be according to these 5 pieces. Okay, so it's just to give you motivation for how you get all covers of degree bigger than or equal to 3. And then the question is, how do you avoid building any other closed one manifold? So how do I avoid the degree 1 and the degree 2 cover? Sorry, my iPad's being all sorts of weird, but that's okay. I am going to just say that I've chosen the pieces. I left out a particular piece, and I chose the gluing rules and the pieces carefully so that all of the closed one manifolds that I can build actually have to contain the 3-piece. Okay, and the 3-piece is long enough that it guarantees that your cover is of degree at least 3. Okay, so this is the general heuristic of like how you take a family of manifolds, find a Lego kit with some gluing rules, and try to say, okay, this is determined by this Lego kit. Okay, so this is sort of the idea of how you actually think about it, but the definition is a little bit more technical. So I said the title of the talk is that you have a local combinatorial characterization. So let me just kind of tell you what a local model is, what it means to be locally combinatorially defined, and then we'll go from there. But throughout, I just kind of want you to keep this picture in mind as what we're aiming for. Okay, so here's the definition of a local model. It's just a triangulation of a ball where you've put down a preferred vertex. So it's a pair KV. And the Lego set now is going to be like the building blocks are going to be finite sets of local models. So this tells you locally what things look like, right? If you're going to build something with M. So let me just give you this definition. If you take a simplicial complex L, then it's modeled on this finite set of local models. If for each vertex in your space, there's a little neighborhood around that vertex that looks like is exactly one of the elements in the kit. Okay, so this is saying that this is locally looking like the pieces in your kit. Okay, so that's what it means to be modeled on M. Maybe one comment that I'll just make is that if L, a simplicial complex, is modeled on M, then any finite covering space of L is as well, because the behavior around vertices is the same, right? That's what it really means to be a covering space. Okay, and here is the definition of what it means to be locally combinatorially defined. Let me know if the margin crap is getting in the way of you seeing anything, because we couldn't get rid of that. So move up. Yeah, I don't want to spoil anything though. Okay, I'm going to give you examples in a second. Is that better? In front of you, I see. Okay, yeah. Okay, so what does it mean for a family of manifolds to be LCD or locally combinatorially defined? It means that you have some finite set of local models, and the things you can build with those local models is exactly the family of manifolds that you were looking for. Okay, so a family of manifolds T is LCD if all the things you can build are elements of T and you can't build anything else. Okay, so you should start to guess that maybe these two things are equivalent. Okay, and in fact, I'm actually going to use a third perspective in just a second to just confuse you all a little bit more. But in fact, it's going to be the easiest one to actually understand. Okay, before I do that, are there any questions? I'm going to give you examples now of LCD sets. Like this is not, we didn't just make this up. There's classical families of LCD sets, and I'll tell you where our motivation really came from. But are there any questions on just the definitions? It's I use G of M for like generated by M, all the closed manifolds that you can build with that kit, for instance. Okay, so the things you can build with the set M are exactly T. That's what I'm trying to say there. Yeah, thanks for asking that question. Like links of vertices. Yeah, exactly. Like little neighborhoods of the vertices. Yeah, exactly. Right.
But just to clarify, with your Lego kit, you actually build simplicial complexes. But when you say a family of manifolds, you mean up to the atomic?
Yeah, I mean, what we really mean is that for like a family of manifolds, right? I take each one in the family. So for T and T, there's a triangulation that has this property. That's what I mean. Okay. No, yeah, it doesn't. Right. So there's like 3 different perspectives that are going to go on now. First is just like the motivational thing. Like you're a kid, you want to build things, right? Like it's a Lego set. This is more refined, and it's why we call it locally combinatorially defined. This does not have gluing rules. It's just about local models. Okay. The third perspective is going to be a branch manifold perspective, and that's where you can see everything. And again, there's 2 parts to every proof that I'm going to talk about today, that you can build all the things you want and that you're not building anything else. And the not building anything else part is the really hard part. And it becomes easier with the third perspective that I'm going to tell you about in a second. Okay. But I will go with some motivational examples first. Any other questions about the setup? Okay. So here are some examples. We already saw this. Oh, sorry. I'm going to scroll up for some people here. Just don't read ahead too much, right? That's the danger when you scroll up. So first, if I just wanted to construct degree covers of like S1 of any bigger than any degree, I would do something similar, right? Like I give you some pieces and I just make it so that all the things I can build at least have some really long piece that would give you covers of only degree K or more, okay? On the other hand, all covers of S1 is another example of an LCD set. So that's easier because I'm not trying to eliminate any lower degree covers, right? And in fact, if you just give me any fixed closed manifold, if you look at the set consisting of all covers of that manifold, that is an LCD set. And this definition is the one where you should be thinking, yeah, we just saw if you can construct this manifold, you can construct all covers of it as well. When we get to the branched things, I'll also tell you like what the idea is for that. Okay. And then, okay, so we're in a 3 manifolds conference, but usually we use motivation from surface theory. I just want to note that if you let Dn be a disk formed by cyclically arranging n triangles around V, and for instance, let's think of D7. So I'm going to take a disk with 7 triangles around the vertex, the center vertex. Then what you can build with this one piece is exactly the set of compact surfaces with negative Euler characteristic. Okay, if I instead change this to a 6, I would build all flat surfaces. If I change it to a 5, I'd build all spherical surfaces. And so that's like one of the main motivators for why we started studying what I'll talk about today. I printed out notes, but I actually think I'm just going to get confused by having my notes here. I was like, maybe it'll help. Probably not. Okay, but here is the real inspiration. Again, I'm like low because I'm trying to make it like suspenseful. Here's the inspiration. It's a theorem of Cooper and Thurston's and independently shown by Walker in 85. And the theorem says that there is a set of 5 local models that they give explicitly in their paper, in the Cooper-Thurston paper, such that every closed-oriented 3 manifold is modeled on J. Okay, I want you to just put a little caution here. So like maybe I'll put like a reddish like note here. That's only one direction of the LCD definition, right? This is saying you can build every closed-oriented 3 manifold with these 5 pieces, but you're probably going to build some non-oriented things as well. I know it's sad. But I think someone could come up with an actual LCD set like without too much work, right? And also Walker reduced this to 3, but I didn't put 3 because I tried to look through his thesis and I didn't see where the local models were. Like this is really, the 5 are really explicit. So yeah, Steve.
You're trying to build 3 manifolds and you don't care about building a bunch of extra garbage. Why can't you just take a tetrahedron, right? Why does that not suffice?
I'm going to avoid that question and say, we should really read the paper together. I haven't like thoroughly gone through. I've just like seen it's like 3 pages, and yeah, I'm not so sure. I've gotten that question once before, and I was, you can build non-manifolds. Yeah. Well, okay, but you can say like, what are all the manifolds I can build with this, right? Yeah, but this theorem is not saying that, right? It's saying that like, sorry, Daniel, what were you going to say? That's true. That's true. Yeah, I think I'm just, I knew this was going to come up and I just want to like kind of let it go and we'll just look at the paper, but this is exactly what their theorem says. Okay. And it is like the reason why we're looking for, again, these local models. Okay. So what are we trying to do? This is a theorem, the main theorem. It's preliminary work, just FYI, everybody. We have some cases that are like fully fleshed out, but some that we're still working on. So the set of closed orientable 3 manifolds that admit a particular Thurston geometry is actually an LCD. So that's 8 theorems in one. There are 8 Thurston geometries. And so the first thing you should try to understand is why this is harder than this. And so the point here is if I want to build all spherical manifolds, well, I can do it using this local model set, but it's going to build that. It's going to build everything else as well. Okay, so to just build exactly the spherical manifolds, to just build exactly the H2 cross R manifolds, that's the hard part. Eliminating the other, I almost said the word immersions because I'm going to talk about immersions later, but eliminating the other manifolds when you're trying to build a construction kit is the hard part. Okay, so I know that, okay, so I'm going to say in a second, how we think about the 8 geometries and which one we're going to focus on today. But I will now introduce that third perspective that I was talking about. Okay. And it's because it's going to make like that the two parts of the theorem, it's going to make one of them easier. So here is the third perspective. And I said make life easier, even though I've given you lots of perspectives already. So my claim is going to be that first example that I started out with. The set of I'm going to claim that the set of closed manifolds, manifolds that immerse in this thing, which looks like a train track. Okay. This is going to be exactly the set of covers of degree bigger than or equal to 3. Okay. So what you're kind of seeing here is that I have this branched 1 manifold. Okay. That's what a train track is. It's a branch 1 manifold. And it kind of looks like it's built from all the pieces that I was using before, because it is, okay? But if you try to build a closed 1 manifold that immerses into here, you have to start somewhere. I'm just going to choose to start here, right? And I'm going to go around until I close up. And there's a few ways that I can go. But each path that I take, each closed path that I take has to traverse a pink piece. And if you remember, the pink piece was the really long one that made sure that your degree was at least 3. Okay, so I've kind of taken that first example and concisely said, okay, here is a branch 1 manifold. And you can start to see that you get all of the covers. Like here is the cover of degree 3. This is 4. This is 5. And then if you want to do 6, you go twice around here. Okay, so you get 3K plus 1. So if I want to do the degree 7 one, I go twice around here and then close up. Or maybe I go once around here and then I close up the second time with this one. Okay. And you can play with that and see that you actually get all the covers that you want. But it's visually much easier to check that you don't get the covers that you didn't want, right? So the branch manifold perspective makes that part much easier because you can actually see what the path has to be. You start somewhere, it has to end at the same spot, and it had to traverse a pink piece. Okay. With the gluing rules, that's much more challenging. You're going through and saying, what are all the possible things I can glue up in all these ways? And that's not as easy as seeing it physically here. Okay, so that's my alternate perspective, is that I want to build branched manifolds that admit immersions of exactly the family that I had started out with. Okay, so what I'm claiming here, oh, sorry, this is all the stuff I just said, which is that you, all the covers you want immerse into this branch thing and no other ones do. Okay, so what I'm claiming here is that there's this equivalence between the local model's definition and the branch manifold definition. And I'm not going to prove this, but it is something that we prove. Okay. The reason why there's so many definitions is because we started thinking of one way, and then we realized that there was another way that made some parts easier. And then we finally landed on this third equivalent definition that made all the parts easier. Okay. Sometimes we do actually use this LCD perspective versus the branched one when there are nice things known about triangulations of manifolds. The branch manifold, yeah, it should be compact. Yeah. So what you're trying to do is take a ton of information, like a huge infinite family of 3 manifolds, and you're trying to put down something that you can just draw. And that actually like encapsulates all the information of that whole family, right? Yeah. If I didn't insist on compactness, I could just put down all the individual manifolds in the family. And then that would be a branch manifold, right? Branch manifolds don't need to be connected. So I just put down the entire list and then I've won, right? You want to be much more clever than that, like draw something really small that encapsulates all of this information. Good question though. Okay, so I realize that people might not have seen branch manifolds before, and I'm going to give a really cheap definition here, which is that a branch manifold is a generalization of a train track and a branched surface. Okay, so here is a picture of a train track. The way you imagine it is that Okay, so what's the defining property of this being a branched one manifold? Most places it just looks like a piece of a one manifold. And then you have this branching locus, right? So this is a branching locus, that's all in the branching locus, where it looks like several sheets of one space have been propped together. Okay, and that's really what a branch manifold is. So here in this picture, what you see is that you have some like a plane here, and a plane here, and the three slices have been glued together in like a portion of this centerpiece, right? So if I'm running through here, I can kind of go in any of these two directions. But notice if I'm running through here, like I should probably be like coming from like, okay, there's like something about the way things are glued up in terms of tangency too, right? Like you don't want to ever take like a sharp corner. Like here, I can go here or here. But if I'm coming this way, I'm not going to go this way. And that's why I'm talking about immersions. That's exactly like something that shouldn't immerse in that train track. Okay. So this is another example of a branch two manifold. It's just two tori glued along a one common edge, a one common simple closed curve. Okay. But again, the idea is most places it looks like a nice n manifold. And then in the branching locus, it looks like sheets of several n spaces glued together. Okay. So that's what a branch manifold is. Let's briefly talk about the 8 Thurston geometries. I know Nathan went through this last week a bit. But here they are. I've kind of grouped them like these two are kind of similar. S2 cross R and spherical, H2 cross R, SL2 universal cover, Euclidean, nil, hyperbolic sole. Okay, so these 6. So what color did I use here? Okay, it's going to be a different color of purple, which will drive me nuts, but probably none of you care. So if I look at these 6, okay, these are all ciphered fibered spaces. Okay, and again, I know Nathan said something about this last week, but those are just circle bundles over two-dimensional orbifolds. So they're generalizations of circle bundles over surfaces, where the base thing is allowed to have like cone points. Okay, and then hyperbolic and sole are just different. And they're not ciphered fibered. But I'm going to focus for most of the talk. I'm actually going to focus on spherical manifolds because. Okay, not because they're the most important, obviously hyperbolic are the most important, but because they're the easiest to start to understand how you do this, right? How you actually construct one branch manifold for spherical geometry that encapsulates all spherical manifolds. Okay. So, like I said, we'll focus on spherical manifolds. Let's just talk about what spherical manifolds are really quickly. So this is like the definition when you're thinking about a geometry. It's a manifold obtained from the universal space, which is S3, and you mod out by a subgroup of SO4 that's acting freely by rotations on the 3 sphere. It turns out that all such manifolds are closed and orientable. That makes this case also much easier. Everything I'm going to talk about today will be about closed and orientable manifolds, but you can do the non-orientable case. It's just quite a bit more difficult. Like you have to keep track of a lot more information. Okay, so that is what a spherical manifold is, but that's not really the perspective that I'm going to focus on. There's something really nice that happens for the ciphered fibered spaces, which is that ciphered fibered spaces admit a particular Thurston geometry based off of 2 numbers. The first one being the orbifold Euler characteristic of the base. Remember, these are circle bundles over base orbifolds. So whether that's 0, positive or negative, that along with the Euler number, which is a rational number, those 2 things actually determine which Thurston geometry your manifold admits. Okay. And I'll just say that the Euler number measures the defect from the particular ciphered fibered space from being a product. It's not an invariant of the manifold, but it's something assigned to the vibration. Okay, so this is the nice chart I always like to keep in mind. Okay, so here again, this is orbifold Euler characteristic. If you're positive and you have 0 Euler number, then you're a product geometry, right? So E measures the defect from something being a product. So when you see that E is 0, you get the 3 product geometries. Okay, the other ones are like the twisted things. They're the non-product geometries affiliated with each of the product geometries. Okay, I think this is like something that just now is ingrained in my mind, and I love this chart. Just like concisely displays 6 of the geometries. So we're going to focus on spherical, of course. Okay, these are exactly those Seifert fibered spaces that are have positive orbifold, base orbifold Euler characteristic and non-zero Euler number. So that's the equivalent definition that I'm going to use. Okay, why does this help me? Because I can take each of these conditions, and especially the base orbifold condition, and I can kind of list out in families what all the possible base orbifolds are. And so that's one thing in spherical geometry that makes life a little bit easier. And that's why I'm starting with that geometry. I'm going to show you the branch manifold now. But before I do, are there any questions just on like focusing in here? Any questions on like the recharacterization in terms of orbifolds and Euler number? The branch manifold for spherical geometry looks like this. Okay, that's obviously not a three manifold. So you're like, what's going on? This is a graphical representation. So this gamma that I'm going to call, okay, and I'm calling it gamma because outside of a couple of places, it's a graph, right? It looks like a train track outside of a few places. And this thing represents the branched three manifold for spherical geometry. Okay, so first, let me just decipher this for you. Every point on a black edge, like this point, this point, this point, this point, anywhere there, that's just a torus, right? I've taken the torus portion and collapsed it to a point. So one thing to note is that if I look at an edge, ignore the labels for now. I'm going to explain that later. If I look at an edge portion like this, that's T2 cross I, torus cross interval. Okay, each of the points represents a torus. And so that's torus cross interval. Okay, the blue dots at the ends are solid tori. And the purple thing is a twisted eye bundle over a Klein bottle, which you don't need to worry about much today. And then maybe the last thing I'll say is what the heck is the green thing in the middle? It's just a four-hole sphere cross S1. Okay, for now, you should think this is all random. Like none of this should make sense, but I'll show you why the pieces are where they are. Okay, and it kind of looks actually like I've taken like two branched pieces and like glued them together. Like there's like a top portion of this picture and a bottom, and you'll see why that is like that in a second. Okay, so the theorem that we prove is that a closed orientable three manifold immerses in that picture, that branched thing, if and only if M is a spherical manifold. And the if and only if is the hard part, obviously. It's a full characterization. Okay, so I'm going to jump a little bit into that base orbifold characterization that I was talking about. So how do I understand all spherical manifolds? I can understand them by the possible bases they can have. Okay, the condition here is coming from just the Euler characteristic of the base being positive. So you just do a calculation. So here's one family and there's another one. So what does this notation mean? This is taking a sphere and you have two cone points of order n. This is a copy of RP2 with one cone point of order n. Also, I don't know why I keep doing this. N is not just greater than 0, n is greater than 1. Okay, otherwise it's not a cone point. Okay, these actually no, this spoiling the surprises. Okay, so those are actually lens spaces. Okay, so in fact, you can just use these. These are like representing like maybe two different ways that you can fiber the same lens space. So we're really going to focus on like S2 and N, okay, but it doesn't really matter. All of these base orbifolds fall into the category of lens spaces. Those are nice. We actually understand them pretty well. Okay, and we're going to focus on those in a second as well. Let me just tell you what the other families are. Again, that should be an N greater than 1. Okay, so the second family is corresponding to the base orbifolds S2 with two cone points of order 2 and one cone point of order N. And these are prism manifolds. They're just quotients of lens spaces. And if you want to play around, this thing actually covers this. It's a twofold cover. And so you have a corresponding covering map on the other side as well. Lens spaces cover prism manifolds. I'm not going to talk too much about those today. And then there's just this other family. Okay, so the sphere with a cone point of order 2, 3, and N, where N is 3, 4, or 5. And again, this is just coming from Euler characteristic calculations. Okay, and that's all of them. So the nice thing again about spherical manifolds is I can break down the base orbifolds into basically 3 different categories. Okay, so what I'm going to do is show you first where the lens spaces are. Okay, so I should first tell you what a lens space is. because, okay, there's many definitions, and I'm just going to use one from Bruno Martelli's book on three manifolds. If you don't like the definition, I'm sorry, that's just the one I'm going to use today because it's easiest for me. But let's just put down some terminology. Okay, actually, let's just show both since I know the bottom part of the screen is not a happy place for anybody. So if you take D2 cross S1, that's a solid torus. And the curve alpha in the boundary torus that bounds the disk is called the meridian. Okay, I think Nathan talked about this a bit last week. So here is a standard solid torus with the standard meridian, where it really just is the classical way we draw it. But there's nothing stopping me from saying, okay, this is another solid torus where I've chosen this curve gamma and I filled that in with a disk, and this is still D2 cross S1. It's just that the meridian is not the classic one. Okay, these are both solid tori. Their meridians are just different. Okay, so let me give you the definition I like of a lens space. It looks long, but in summary, it's two solid tori glued together, okay, with one condition. So a lens space is obtained from two solid tori. Sometimes when I reveal things, letters go missing. So it's taken from two solid tori A and C. You glue their boundaries together, subject to the condition. Okay, subject to the condition that the meridian of alpha is not equal to the meridian of, the meridian alpha of A is not equal to the meridian gamma of C. So I can glue these two solid tori together and get a perfectly fine lens space. Okay, I'll leave it as an exercise to sort of see what base orbifold do you get if you use different gamma and so on and so forth. Okay, but this is a perfectly fine definition of a lens space. And so what we need to do in our branch manifold is to say, okay, I have to take all possible ways subject to this condition of gluing two solid tori and see it somewhere in the branched manifold, right? Like, where do they end up? Where do they land? Okay, so the first thing I'll say is that if I fix the first torus, the first solid torus to be the standard one, right, where it has the standard meridian, that's how I think of A. Then in a basis for the boundary of the other torus, this curve gamma is some PQ curve where P and Q are co-prime. And because we don't want meridians to be equal, PQ is not equal to 1, 0. So what I'm saying is that 1, 0 is this standard meridian curve. And then the gamma curve is a PQ curve on the other torus. Okay. And there's something special about how we can get to all those PQ curves. So maybe I'll ask a question first. Now that you know the definition of a lens space, okay, where in this picture could you possibly put a lens space? So just a reminder, the green thing in the middle is a 4-hole sphere cross S1. The blue things are solid tori, and the purple thing is a twisted eye bundle over a Klein bottle.
And the labels, by the way, are like right to left to
We're going to get to those. I know Genevieve is excited. Ignore the labels for now. That's going to come of like, how do I get all of them, right? But does anybody have a guess? The top horizontal line is right. Yeah, so you're almost thinking if I just go straight across, it's looking like, okay, what's the fact that I'm using? If I take a solid torus like this, and I union with the torus cross interval, I'm just fattening it a little bit more. And so I still have a solid torus. So this whole thing, ignore the label. This is just a solid torus, and then I'm gluing it to another solid torus. So that's right. That's exactly where a lens space could go. And now you have to start asking, what is going on with the labels, right? So the labels should be encapsulating all the ways that I can change the slope of the meridian to be a PQ curve, right? Every PQ curve. So let me just tell you what these matrices are. Okay, L is going to be 1, 1, 0, 1. R is going to be 1, 0, 1, 1. Those are in SL2Z. And then just notice how they act on a vector. Okay, L of AB is A plus BB, and R applied to AB is A plus A and then A plus B. Okay, so here is my claim. It's that if I take any PQ vector with P and Q coprime not equal to 1, 0, then there exists a matrix Q that can be written in this regular language where I just start off with the matrix R and then do any combination in that group generated by L and R. And Q applied to 1, 0 is going to be PQ. Okay, so why should you believe this? These matrices are really doing the reverse of the Euclidean algorithm. Okay, Euclidean algorithm is you take one of the things, take the bigger, the smaller, and you subtract it and you keep going, right? And this is the opposite, it's adding them, right? And so here, what you can imagine is I'm saying from any PQ that are co-prime, I can get down to 1, 0. So I'm just doing it in reverse, right? If you give me a particular PQ, like this example, okay? So if I want to get to 2, 1, I know that there is some matrix in R times LR that can get me there, okay? Because I'm reversing the Euclidean algorithm. Okay, actually, let me just show you what the matrix is because, okay, it's just L times R. Okay, so notice it always has to begin with the R because the regular language had that on the right hand side. But here I could do anything, and then I should be able to get to different PQ vectors. Okay, so what that means is that exactly what we said is correct. If I want to get any lens space, oh man, I didn't want this here. Okay, let's get rid of that part. Okay, so if I want to get any lens space, it's going to immerse in this spherical branched manifold with an immersion path starting and ending at x5 and x2. Okay, so to get this one, I have a laser and I'm not using it. So let me actually show you. To get this, to get the lens space where I'm taking one solid torus with the standard meridian and gluing it to the other solid torus with the vector 2, 1 as the meridian, I would go start here, go over L. We're going to ignore the 2s as well for a second. Okay, I start here, I go over R, I go over L, and then I'm actually just going to ignore the fact that I'm undoing that 2, and then I close up here. Okay, so if I didn't have 2 labels anywhere, I'd just go like this, right? But the 2s are doing something that I'll explain in a second. Okay, but if you give me a different PQ vector, maybe the path would be something like R, L, R, 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 L, and then I close up, right? And that's how I find all the lens spaces. In this small piece of information, this small piece of the branch manifold, I have all of these infinitely many lens spaces. Okay, and then the one thing that we always have to remember is, what about the other part of the proof, right? Like why don't I have, oh, is that, okay, good. Why haven't I like let something else accidentally immerse into there, right? And so maybe what I'll just say here, and I'll put this in, I'll let you read both parts, a little treat. So I'm just going to say we've taken precautions so that S2 cross S1, which is not a spherical manifold, right? It's an S2 cross R manifold. We've taken precautions so that that doesn't immerse in the branch manifold we constructed. And that's why there's 2s everywhere. Okay, so what is the idea of this 2, right? Why do I have the 2 showing up, the 2L, the 2R? It's so that I can't take T2 cross I and just glue here. Okay, here's a schematic that shows you why that's impossible in a dimension lower. Can you all see if I just draw over here? Let's say I take a tube and then I glue on an annulus to this curve. So let's say this is alpha and this is A1 and A2. Okay, suppose I glue A2 to alpha using a degree 1 map or a homeomorphism, whatever you want to call it. And then I glue A2 here using a degree 2 map. Okay, what does the resulting manifold look like? Okay, so you have this branching here, right? But if you try to immerse something in this tube, it's not going to be that a torus, okay, a torus cannot go into that part. When you come back around, you've taken a degree, you're taking a curve and gluing it to another curve 2 times around. And so you don't get a manifold, right? So the doubling thing is to say, I can't just take this loop and traverse it and get a closed manifold because I don't like those. I don't want S2 cross S1 to immerse into my branch manifold. So what I do is I apply this 2 is like a doubling map. So when I come back around, one torus is glued to the other torus using a degree 2 covering map. And that means torus cross interval is not just going to glue into there to become T2 cross S1, or sorry, S2 cross S1. Okay. So those doublings are like the secret sauce that's like getting rid of unwanted immersions. Because anytime you see a loop, it's dangerous. That could be an unwanted immersion. I really want only the things that go from this endpoint and end at this endpoint. Okay, so because I have put all those 2's everywhere, what that tells me is that the only closed manifolds that immerse in this branch manifold have to have immersion paths. Okay, that's like a vague thing of what I'm saying, but it's really like, where do you see the immersion, right? Like this could be an immersion path or something like that. Okay, they can only have endpoints being the blue dots and the purple dot. Okay, so we saw perfectly valid immersion paths with the 2 blue dots, and I'll show you the other ones and what they correspond to in a second. But that's really what like all the 2's are eliminating, is bad unwanted manifolds. Really, it's eliminating S2 cross S1. Oh yeah, that's a good point. So I do need to pick up some R's and L's, right? So again, I'm going to get out of the way of the projector. So let's say I did want to do the matrix that I said before, LR, right? So when I go around here, I'm not saying that I can't traverse this path. I can, but I have to keep going. The issue is, before I can glue up to the other solid torus on the other end, I better undo that doubling. Otherwise, I still don't have a manifold. So what I do is I traverse the 2 in the opposite direction, and they undo each other. Okay, literally as matrices, it's like multiplying by 2.5. But you can think of it as like you're applying the double, and then you're applying the covering map coming back down to undo the bad thing that you did somewhere else. So as many times as you might go around, let's say I go R, L, R, L, and then I try to go, well, no, actually, I should go the right number of times back around there before I close up to undo the doublings that I did. I doubled, so I better undo that 4 times and then go to the end, and then I get a closed manifold. Okay, so what I'm going to do is just show you that this was the one that gave all the lens spaces, okay? This portion gives the prism manifolds. The only difference between prism manifolds and lens spaces is that you're gluing a twisted eye bundle over a Klein bottle, which has a torus boundary, to a solid torus instead of 2 solid tori together. Okay, but you're still subject to the same condition. The meridians, it's not really a meridian on that thing, but the curves that are special are not going to get glued together. Okay, so these are the prism manifolds. So category 1, category 2, and then ugly category 3, which is, it's funny because this is the simplest category to kind of like describe, but it gives the most complicated picture. Okay, so what's going on here is you're looking for a sphere with 3 cone points. So I'm just going to ignore this part. No, actually, I do want to cover it. So I'm just going to ignore this part. And these 3 things give the cone points. This is going to give the cone point of order 2. 2 different ways you can get a cone point of order 3, and then cone points of order 3, 4, and 5. Okay, this thing adjusts up the Euler number because we're only doing finitely many different things here. We're saying maybe this has a 1/3 slope and a 2/3 slope, but if I want to account for like the 4/3 slope, I should adjust up the Euler number. This is mostly for experts, I'm saying. Okay, so what you should just really take from this is that third family all goes into this, and nothing else goes into this. Okay, so those are all the pieces of the branch manifold. I'm going to briefly talk about the other geometry, so I'm going to pause before then to see if any. Michelle, yeah. It's a good question. Oh, the question was, can you read the fundamental group from the path that you pick? And I think like in this case, I want to say you can, but I'm not really that sure. Does anybody else have an idea? Like, okay, I'm taking a 4-hole sphere across S1, and here I'm actually deciding like which Jane filling I'm doing. So if you know the exact slope, you should be able to read off the fundamental group, I think. Yeah, I think so. For the lens spaces, it's a bit easier because they have really simple fundamental groups. So yes, for that. Yeah. Yeah, Edgar? Yeah, maybe. I mean, I think Michelle was meaning really read it off by just the path, right? But like you can definitely do. Okay, yeah, definitely you can take like, okay, for the lens space example, just like decompose it into the 2 halves, like the ones, okay, anyway, yes, I think the answer is yes. Okay, any other questions on the spherical case? Okay, I'm just going to say a few words about the others. Obviously, I'm not going to give a whole, it'd take me hours to do the rest of them carefully, but there's some that are easier. So remember, we're trying to take a ton of information and like show it all in a tiny branch manifold, right? Well, some of the geometries are really easy in that sense because there's only 2 S2 cross sorry, there's only 2 S2 cross R manifolds that are closed and orientable. There's only 6 Euclidean manifolds. So what's the branch manifold that I would use for these? Just those, like the disjoint union of the 6 of them. That's a perfectly fine branch manifold. It happens to not be branched. If you want to glue them together in some way, by all means, go ahead and do it, right? But that's it. These are the 2. You just take whenever you have a finite family of manifolds, it's easy to show that they're LCD. You just take the branch manifold to be the family of manifolds itself. Here's the Sol branch manifold. So Nathan, I don't know if you mentioned this, but Sol geometry is consisting of all torus, bundles, and semi-bundles. So I asked this question in another talk I gave, like, oh, what do you think is the hardest geometry? And someone was like, Sol, which like is a good guess, but actually think about like the algorithms we've been playing with, right? If you want to build torus bundles, you have to take torus cross interval and glue left to right using some matrix. But actually that part we've kind of seen is easy to encode with some regular language stuff, right? The reason why this picture is a little bit more complicated is because you have to get the semi-bundles in there as well. Okay. Here is what I've been spending all of my time doing lately. This is a surprisingly difficult thing. H2 cross R versus SL2 geometries. Okay, the thing to remember here is that the base orbifolds in these 2 families have negative Euler characteristic. The thing that's horrible about that is that there's no nice breaking into 4 families, right? If you look at all of the base or all of the orbifolds with negative Euler characteristic, it's a wild family. So first you kind of have to understand, how do I make that into like a branch surface? And then how do I build all of my manifolds from there? The issue is that differentiating between these 2, when they have often the same base orbifolds, and in one you just break the product structure, and in the other one you don't, is that you somehow have to find a way to like show there's a horizontal surface so that you're in a product geometry, or show that you've broken any possible horizontal surface and you're in SL2 geometry. Okay, so the pictures, just really quickly for that. Both of them are built from these things. You could just ignore these little guys. This is branched person and branched babies. But this branched person is like the generic case. So actually, when you look at all of these orbifolds with negative Euler characteristic, there's a generic case when you have like maybe lots and lots and lots of cone points. And then there are exceptional cases. Each of these is just representing an exceptional case. It like makes the picture messy for like almost no good reason. Okay. If you understand this picture, you actually understand everything in some sense. So what this is a 1, 2, 3, 6-hole sphere. Again, these are torus cross intervals, the matrices. Oh, yeah, actually that's good. 2 times I. And then this is still a twisted I bundle over a Klein bottle. This is something slightly different because of the horizontal surface thing, but this really is like a T2 cross I that's been glued in a very particular way. And the 2 ways to sort of edit this is to say, again, for the experts, I'm either going to take this like boundary component and extend the horizontal surface past this boundary component and fill it in, or I'm going to break the product structure at this point. And so I do one of 2 things, and I get these 2 branch manifolds. So one of them, I just filled in the solid torus in some sense, but there's something like a little sinister going on underneath here. Like I'm making it sound like it's easy, but to be able to construct the branch manifold that picks out the horizontal surface here is quite challenging. Okay. And I know this kind of looks maybe a little bit familiar. This is like all other ways of filling so that you don't extend the horizontal surface structure and you break the product structure to get SL2 manifolds. Okay, I'm going to stop there. Dave, Sammy has a question. Go ahead. Yeah. Yeah, okay. So it's by far the hardest case. And so there's a little bit of trouble there. And the first question is, can you just draw a nice picture of a branch fold like this? And unfortunately, the answer is like, not maybe definitively no, but like, that's not how we're going to do it. We're going to build like the thick part using some local models. This is like editing some work of Breslin on triangulations of the thick part of hyperbolic manifolds. And then we're going to use, we're going to take the thin part and fill those in a certain way using 2 different types of solid tori, bounded and unbounded. So it's going to be easier to use the LPD definition for the thick part and easier to use the branch manifold definition for the solid tori that you're filling in. Okay, but it's extremely complicated. That's the sketch. Yeah.
For the sulfates, how do you, because it's on the right, but you have to make sure that it's enough on that.
Yeah. Yeah. So yeah, that's a good idea. So a good question. Sorry. So that's coming in with what matrices I'm using, right? So this S is something new and it's some combination of L's and R's. And so the goal is to say, find a regular language for Anosov maps. And you can do that. Yeah. It's not going to be the same language, of course, because Anosov maps are much more complicated than just any old torus map, but you can do it. Yeah. Yeah. I didn't hear the first part of your question. Will it help us with what? Oh, well, I don't know. Who just talked about the canon conjecture like last week? Yeah, there you go. Daniel should tell me. Oh, yeah. Okay, there you go. Yeah. 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 Okay. Yeah. Edgar? Yeah. Okay, so admittedly, Daryl wrote down the language, but I think it's something that is known. Like, I don't think we made that up, right? Like, it's something that has been constructed before, but it's in our paper, so I can show it to you. Yeah, yeah. It's really hard to hear with the chair squeaking. So you're saying like, so. Okay. Oh, I see. I think yes is the answer. I think we think the answer is probably yes. Like we don't know for sure, but it seems like it's almost exactly corresponding to something like that, at least for some of the models, right? Like maybe not all models can be described like that, but yeah, for some of them, it looks like you could probably.
There are no other questions. Let's thank Priyam again.